we have our next topic, the motor principle or the DC motor. So, an electric motor is a machine which converts electric energy into mechanical energy. So, the generator is the opposite of the motor. Its action is based on the principle that when a current-carrying conductor is placed in a magnetic field, it experiences a mechanical force whose direction is given by the Fleming's left-hand rule. So this one is our conductor, and this is the stationary part, the north and south pole. So the rotating part is our conductor, and it is connected to a source EMF or the battery. So constructionally, there is no basic difference between a DC generator and a DC motor. In fact, the same DC machine can be used interchangeably as a generator or as a motor. DC motors are also like generators, shunt wound or series wound, or a compound wound. In figure 29.1, a part of multipolar DC motor is shown. When its field magnets are excited and its armature conductors are supplied with the current from the supply mains. So this is the conductor supplied by the battery or the supply mains. They experience a force tending to rotate the armature. The armature conductors under N pole are assumed to carry current downwards, or the crosses, this one, downward, and those under S poles to carry currents upwards, or the dots. So this dots here represents upward motion, and the positive here or the plus sign represents the downward motion. By applying Fleming's left-hand rule, the direction of the force on each conductor can be found. It is shown by small arrows placed above each conductor. It will be seen that each conductor experiences a force F, which tends to rotate the armature in anti-clockwise direction. These forces collectively produce a driving torque, which sets the armature rotating. It should be noted that the function of a commutator in the motor is the same as in the generator. By reversing current in each conductor as it passes from one pole to another, it helps to develop a continuous and unidirectional torque. When something like a refrigerator or an air conditioner, anything machines that has a motor, first turns on in your house, the lights often dim momentarily. To understand this, realize that a spinning motor also acts like a generator. A motor has coils turning inside magnetic fields, and a coil turning inside the magnetic field induces an EMF. So this EMF is known as the back EMF. It is act against as the applied voltage that causing the motor to spin in the first place and reduces the current flowing through the coil of the motor. At the motor's operating speed enough, current flows to overcome any losses due to friction and other sources and to provide the necessary energy required for the motor to do work. This is generally much less current than is required to get the motor spinning in the first place. The term back electromotive force, or just the back EMF, is most commonly used to refer to the voltage that occurs in electric motors where there is a relative motion between the armature of the motor and the magnetic field from the motor's field magnets or windings. So here we can see that the equation of the armature current is equal to the net voltage divided by the armature resistance, or equal to the terminal voltage minus the back EMF EB divided by the RA. Or simply, we can rewrite this equation. Terminal voltage is equal to the back EMF plus IaRa for shunt generators. Or EB is equal to terminal voltage minus the drop in the armature resistance. So EB, same in the equation in the EG in our generator, EB is equal to Zephon divided by 60A. So, our N here is in RPM kasi may 60 tayo dito sa baba. So, A is the parallel path. It can be lap or it can be wave winding. AW. Pag lap, MP. Pag wave is 2M. Twice the multiplicity. The voltage V or the terminal voltage applied across the motor armature has to overcome the back EMF, EB. So our applied voltage must be greater than the back EMF of the motor. Number 2 is supply the armature ohmic drop IaRa. So our terminal voltage must supply the ohmic drop of IaRa. Terminal voltage is equal to the sum of the back EMF plus the drop in the armature, which is IaRa. So this is known as the voltage equation of the motor. We now multiply both sides by current Ia. So we will get VIA is equal to EBIA plus the square of the Ia multiplied by armature resistance. So our terminal voltage multiplied by the armature current, it is the electrical input to the armature. EBIA, electrical equivalent of mechanical power developed in the armature. Ia squared Ra is the copper lost in the armature. So hence, out of the armature input, some is wasted in I square R loss and the rest is converted into mechanical power within the armature. The gross mechanical power developed by a motor is PM. So it is equal to terminal voltage times armature current minus the copper loss. Differentiating both sides with respect to Ia and equating the result to 0, we get V is equal to EB plus IaRa and IaRa is equal to V over 2. Therefore, the back EMF is equal to terminal voltage divided by 2. This is the condition for maximum power. So thus, gross mechanical power developed by a motor is maximum when back EMF is equal to the half of the applied voltage. So this condition is, however, not realized in practice because in that case, current would be much beyond the normal current of the motor. Moreover, half the input would be wasted in the form of heat and taking other losses, such that the mechanical and magnetic losses. The more efficiency will be well below 50%. This is the circuit diagram of the different types of motor. First is the shunt motor. Same circuit diagram in generator. Ang nagkaibahan lang ay yung direction ng currents. So, in generator, we call this one as terminal voltage, but in motor, we will call it as source voltage. So, source voltage, we have a current here, which is Im, the current of the motor. because this source voltage will supply the motor and its resistance and windings. So this is the direction of your IM. It is towards the node. And then your IA is downward. We have here your RA. Sometimes it is drawn inside this motor. Okay. Also, the direction of RSH, the same in generator, downward. RSH is the shunt resistance. ISH is the shunt current. Shunt current is equal to, this is Vs, source voltage divided by the shunt resistance. From KCL at this node, IM is equal to IA plus ISH. And our back EMF for shunt is equal to the source voltage minus the drop in your resistance, armature resistance, IARA. In shunt, unless otherwise specified, the flux of the motor is assumed to be constant. Next type is the series motor. So series motor, the series resistance and the armature resistance are connected in series. Again, the direction of the motor current upward, and then since RSE and RA are in series, therefore our ISE, it is equal to your IM equal to your IA. So EB is equal to the source voltage minus the drop in RSE and the drop in your RA. So in series motor, flux is directly proportional to the armature current. So nandito yung flux sa loob ng motor. It is directly proportional to the armature current. For long shunt compound motor, this is your source voltage in parallel with the shunt resistance, and then the RSE and RA are connected in series. So RSH is in parallel with RSE plus RA. Therefore, the current in the series resistance, it is equal to the current in the armature resistance. From this node again, KCL, IM is equal to IA plus ISH. Shunt current is equal to the source voltage divided by RSH. Therefore, the back EMF is equal to the source voltage minus, again, the drop in RSE plus the drop in RA. For short shunt compound motor, we have here the series resistance in series with the source voltage, and RA is in parallel with the shunt resistance. Therefore, the series current is equal to the motor current kasi series na lang nito. At this node, you can use IM or ISE that is equal to IA plus ISH. So ISH, you can solve ISH is equal to source voltage minus, you will take a loop here outside. Tap nun maalam ni ISH. So ISH is equal to source voltage minus the drop in ISE RSE divided by RSH. The back EMF now will be equal to source voltage minus ISE RSE minus IARA. Example, a 220 volt DC machine has an armature resistance of 0.5 ohm. If the full load armature current is 20 amperes, find the induced EMF when the machine acts as, number 1 is generator, number 2 is as a motor. So in figure 29.7, we have the circuit diagram for generator and motor. So for generator, machine supplies current into the load. So kaya ganun yung direction ng current. While in the motor, we have an external source of Vt equal to 220 and it will supply the motor. Kaya ganito yung direction ng current sa source. So we have here in generator what we call the generated EMF, and in motor we have the back EMF. So the armature current here equal to 20 amperes and the armature resistance is 0.5 and 0.5. Find the induced EMF or find the generated EMF in generator and the back EMF in motor. So for generator, we have EG is equal to terminal voltage plus the drop IA, RA equal to 220 plus IA is 20 times 0.5. So that's equal to 230 volts. While in motor, EB is equal to the terminal voltage minus the drop. So 220 minus 20 times 0.5. So EB is equal to 210 volts. Next example, a 25 kilowatt 250 volts DC shunt generator has an armature and field resistances of 0.06 ohm and 100 ohms respectively. Determine the total armature power developed when working as a generator delivering 25 kilowatt output and as a motor taking 25 kilowatt input. So we have two cases here, in generator and in motor. We will solve the armature power developed or the EG and EB. EGIA and EBIA, should I say, kasi power. Unahin natin yung generator. So, generator. This is a shunt generator. Our output power here is 25 kilowatts. So, output power or power at the load. Masosolve natin dito yung IL is equal to terminal voltage divided by or PL divided by terminal voltage pala. PL divided by terminal voltage equal to 25 divided by 250 volts. So, IL natin is 100 amperes. The equation in generated voltage of a shunt is terminal voltage plus IA RA. So, terminal voltage is 250 volts plus our IA. Anong value ng IA natin? In shunt, so IA is equal to shunt current plus the load current. Shunt current is equal to terminal voltage divided by RSH. So 250 divided by 100 plus IL is 100. This is equal to 2.5 amperes. So 250 plus 2.5 plus 100 equal to 100, 2.5. 102.5 times RA is 0.06. That is equal to 256.15. So, power developed in the armature, PA is equal to EB or EGIA. So, 256.15 multiplied by IA (102.5) equal to 102.5 equal to 26.26 kilowatts. For motor, we have the current in the motor or input current in the motor. We have input power, which is 25,000 divided by source voltage 250 volts equal to 100 amperes. From our discussion earlier, IA for shunt motor is equal to the motor current minus the shunt current is equal to 100 minus 250 divided by 100, that is 97.5 amperes. Back EMF is equal to the source voltage minus the drop, IARA, that is equal to 244.15 volts. For the armature power now developed in the motor, it is equal to the back EMF multiplied by the armature current, 244.15 times 97.5, that is equal to 23.8 kilowatts. Next is the torque. So by the term torque, it is meant the turning or twisting moment of a force about an axis. It is measured by the product of the force and the radius at which this force acts. Consider a pulley of radius r in meter acted upon by a circumferential force of F in Newton, which causes it to rotate at n, or the speed, which is in RPM. So in figure 29.10, it is illustrated that we have a force acting on this pulley at its radius and at a speed of n, which is in RPS. Then torque T is equal to the force multiplied by the radius. This is in Newton meter. Work done by this force in one revolution is equal to force multiplied by the distance, so that is equal to F times the distance is 2 pi r which is in joule kasi work. So, power developed in this pulley is equal to the force multiplied by the distance, 2 pi r multiplied by the speed. So, the unit is in joules per second or in watts. So, F times R is equal to 2 pi n watt. Now, 2 pi n is the angular velocity. We will express this one in omega, in radian per second, and F times R is your torque. So, therefore, the power developed is equal to the torque, which is F times R, multiplied by the angular velocity, or P is equal to T omega. It is expressed in watts. Moreover, if N is in RPM, then kasi etong omega natin dito is naka-RPS. So, mag-divide tayo ng 60 so that it will become RPM. So, our omega na will be 2 pi n divided by 60 radians per seconds. So, P is equal to 2 pi n over 60 times T, or P is equal to 2 pi over 60 NT, or NT divided by 9.55. In terms of torque naman, T is equal to 9.55 power developed divided by N. So, power developed natin sa previous topic natin or previous discussion, it is equal to EB IA. Armature torque of a motor. Let TA to be the armature torque developed by the armature of a motor running in RPS. If TA is in Newton per meter, then power developed is equal to TA times 2 pi n in watts. So, we also know that the electrical power converted into mechanical power in the armature. So, it is equal to EBIA in watts. So, equating the equation 1 and 2, we will get TA multiplied by 2 pi n is equal to EBIA. So, since EB is equal to flux conductors times speed multiplied by the number of poles divided by the parallel path, we have TA is equal to 0.159 flux multiplied by conductor IA times P all over A in Newton meter. From the above equation, for the torque, we find that armature torque is directly proportional to flux multiplied by the armature current. So, as the flux and armature current increases, the armature torque also increases, vice versa. So, in case of a series motor, flux is directly proportional to armature current, because field windings carry full armature current. Therefore, the armature torque is directly proportional to the square of the armature current. For shunt motors, flux is practically constant. So, therefore, the armature torque is directly proportional to armature current. So, armature torque is equal to the back EMF multiplied by the armature current divided by 2 pi n. This armature torque is in RPS. If N is in RPM, then armature torque is equal to 9.55 EBIA all over the speed in Newton meter. So, the speed here now is in terms of revolutions per minute. Okay? So, next one is the shaft torque. or the TSH. The whole of the armature torque, as calculated above, is not available for doing useful work because a certain percentage of it is required for supplying iron and friction losses in the motor. The torque which is available for doing useful work is known as the shaft torque. So it is called because it is available at the shaft. So this is the output torque. Other terms, the output torque. The motor output is given by TSH multiplied by 2 pi n in watts, provided shaft torque is in Newton meter and n is in RPS. So TSH is equal to output in watts divided by 2 pi n. This is in RPS. If you want to get the RPM or use the RPM of the speed, we will divide the 2 pi n by 60 and you will get 9.55 multiplied by the output all over speed in Newton meter. So remember, pag may 9.55 ka na dito na multiplier means your speed is in RPM. The difference between the armature torque and the shaft torque is known as lost torque and is due to iron and friction losses of the motor. Note, the value of the back EMF can be found from the equation EB is equal to our source voltage minus IARA for shunt, and it is different from other types of motors, and also the formula back EMF is equal to the Zphon over A, or flux Zn times number of poles divided by the armature parallel path A. Parallel path in lap or in wave winding. Example, a DC motor takes an armature current of 110 amperes at 480 volts. The armature circuit resistance is 0.2 ohms. The machine has 6 poles and the armature is lap connected with 864 conductors. The flux per pole is 0.05 Weber. Calculate the speed and the gross torque developed by the armature. I listed all the given parameters here, and the required is the speed and the TA. Before solving the speed, we will first solve the back EMF, that is equal to source voltage minus IARA, equal to 458 volts. From our formula, EB is equal to ZP flux N divided by 60A, we will cross multiply so that we will get the speed. So speed is equal to 60 multiplied by the back EMF times MP kasi lap winding divided by number of conductors times number of pole and flux per pole. Our speed is equal to 636.111 RPM. Power developed in the armature is equal to the back EMF multiplied by the armature current, that is equal to 50,380 watts. Solving now the armature torque, that is equal to 9.55 times power developed divided by speed, that is equal to 756.36 Newton meter. Second example, determine developed torque and shaft torque of 220 volts for pole series motor with 800 conductors, wave connected, supplying a load of 8,200 watts by taking 45 amperes from the mains. The flux per pole is 25 milliweber and its armature circuit resistance is 0.6 ohm. So we have given parameters here listed. Our source voltage is 220, number of pole is 4, number of conductors is 800. The parallel path is wave, so 2m. The output power or the power consumed by the motor is 8,200 kilowatts. It is the load or the output power. Flux per pole is 25 milliweber. The motor current is 45 amperes and armature resistance is 0.6 ohm. Required is the armature torque and the shaft torque. So armature torque 9.55 times power developed divided by the speed. Shaft torque is 9.55 times the output power divided by the speed. So in series motor, we have armature current is equal to our current in the motor kasi series. So back EMF is equal to the source voltage minus the drop. So that is equal to 193 volts. Computing the speed, that is equal to 289.5 RPM. Power developed is EBIA, so that is 8,685 watts. Solving now the armature torque, that is 9.55 times 8,685 divided by 289.5 equal to 286.5 Newton meter. The output power of the motor is 8,200 watts. The useful torque, the shaft torque, is equal to 9.55 times 8,200 divided by 289.5, that is 270.5 Newton meter. The difference between the TA and TSH is the losses in the motor. So basically, TA is greater than your useful or shaft torque. Another example, at 220 volts, DC shunt motor runs at 500 RPM when the armature current is 50 amperes. Calculate the speed if the torque is doubled, given that RA is 0.2 ohms. So we have a given, our source voltage is 220 volts, armature current is 50 amperes, armature resistance is 0.2 ohm, the speed is 500 amperes. So required is the speed if the torque is doubled. Since in our previous discussion, we said that the armature torque is directly proportional to the armature current multiplied by the flux in shunt motor. Since flux is constant here in this problem, we can say that armature torque is directly proportional to the armature current. Therefore, we will equate TA1 at condition 1 divided by TA2 equal to armature current at condition 1 divided by armature current at condition 2 kasi they are in proportional. So, in torque armature 1, the same, and in torque armature 2 is doubled. So 2 times the original, which is the TA1, it is equal to IA1 natin is 50 amperes divided by IA2. So solving IA2, it is equal to 100 amperes. Cross multiply. We can solve back EMF by Zephon divided by 60A. And since flux is constant, the conductor's number of poles and the parallel path is not given in the problem. Therefore, we can say that the back EMF is directly proportional to the speed. So, this means that if the speed increases, also the back EMF of the motor will also increase. Same is true with the speed decreases, the back EMF will also decrease. EB1 all over N1 is equal to EB2 over N2, or EB1 all over EB2 is equal to N1 over N2. So, pareho lang sila. EB1 is equal to 220 minus our initial current, armature current, 50 times 0.2, equal to 210 volts. So, after the torque was doubled, our EB2 now will be equal to 220 minus 100 times 0.2. That is 200 volts. So, equating now our EB1 all over EB2, or EB1 all over the speed N1 is equal to EB2 all over the speed N2. Solving for N2 equal to 476.19 RPM. Next, a DC series motor takes 40 amperes at 220 volts and runs at 800 RPM. If the armature and field resistances are 0.2 ohm and 0.1 ohm, respectively, and the iron and friction losses are 0.5 kilowatts. Find the torque developed in the armature. What will be the output of the motor? So we have here the given. The armature current, since this is a series motor, the current motor, it is equal to armature current equal to 40 amperes. Speed at 800 revolutions per minute. RSE is 0.1 ohm. Source voltage is 220 volts. Armature resistance is 0.2 ohm. The iron and friction losses is 0.5 kilowatts. Required is the armature torque and the output power. Solution. Our working equation to get the armature torque is 9.55 multiplied by the armature power divided by the speed, or 9.55 it is equal to EBIA divided by the speed. Solving first the back EMF equal to source voltage minus the sum of RA plus RSE, since they are in series, multiplied by the armature current, that is equal to 208 volts. Solving for armature power, that is equal to EBIA. 208 times 40 equal to 8,320 watts. Solving for armature torque is equal to 9.55 times PA is 8,320 divided by 800 equal to 99.32 Newton meter. Next, we'll compute the total losses in the motor. Total losses is equal to the copper losses or copper loss plus the iron and friction losses. The total resistance in our motor is the sum of the armature resistance and the series resistance, that is equal to 0.3 multiplied by the armature current, which is 40 squared, plus the iron and friction losses equal to 500 watts, that is 980 watts. Solving the motor output, it is equal to the input power minus the P losses. Our input power is equal to the source voltage multiplied by the current in the motor, or IA, minus the P losses. So, input power is equal to 220 times 40 minus 980. It is equal to 7,820 watts. So, this is the output of the motor. Next, a 4-pole 240 volts wave-connected shunt motor gives 11.19 kilowatts when running at 1000 RPM and drawing armature and field currents of 50 amperes and 1 ampere respectively. It has 540 conductors. Its resistance is 0.1 ohm. Assuming a drop of 1 volt per brush, find the total torque. Total torque is the armature torque. Useful torque is the shaft torque. Useful flux per pole, rotational losses, and efficiency. So I've listed all the given. Number of pole is 4. Parallel path is 2M. Output power is 11.19 kilowatts. Speed is 1000 RPM. Armature current 50 amperes. Armature shunt current is 1 ampere. Number of conductor is 540. Armature resistance is 0.1. And the voltage drop in the brush is 2 volts. Solving for armature torque, we have 9.55 times EBIA divided by the speed. So we will solve first the back EMF. That is equal to 233 volts. So 240 minus the drop in the armature minus the voltage drop at the brush. So that is 233 volts. TA now will become 9.55 times 233 times 50 divided by 1000. So armature torque is 111.258 Newton meter. For the useful torque or the shaft torque or output torque, 9.55 times output power divided by the speed. So 9.55 times 11.19 kilowatts divided by 1000, that is 106.86 Newton meter. Solving for the useful flux, from our formula, EB is equal to Zephon divided by 60A. So flux per pole is equal to 0.0129 Weber. Next, I will discuss to you the power stages. So this one is for generator. And this upper right here is the flow for motor. Power stages for motor. It is just the opposite of the generator power stages. So we have here the electrical power output. In motor, we have the source voltage multiplied by the motor current minus the copper losses, that will be equal to the power developed in the armature. You can solve this power developed in the armature also by multiplying the back EMF and the armature current. So power developed in the armature minus the iron losses, iron and friction losses, that is equal to the mechanical power input or the output of the motor. Okay, so solving for the iron and friction losses from our power stages, ito. So that will be equal to power developed in the armature minus the mechanical power input or the output power of the motor, that is equal to the iron and friction losses. First, we will solve the EBIA, that is equal to armature power, so 233 times 50 amperes, minus our output power, that is given 11.19 kilowatts. So subtracting these two, you will get 460 watts, equal to the iron and friction losses of the motor. So solving for the efficiency, efficiency is the output power divided by the input power times 100%. Our output power is 11.19 kilowatts and the input power of the motor is equal to the source voltage times the motor current. So 11.19 kilowatts divided by 240 times our IM here is the sum of the armature current and the shunt current. from our previous discussions. So that is equal to 91.422%.